The goal of this section is to understand more about OpenCL, how it is used in Vitis, and to understand the OpenCL execution model for Xilinx accelerators. OpenCL, or Open Compute Language, is an open standard framework for writing programs that execute different heterogeneous platforms. OpenCL can be used to write code for CPUs, GPUs, FPGAs, and other devices. Many different companies provide support for OpenCL, including Xilinx. OpenCL is based on C and C++ and provides an API for programming, controlling, and executing programs on these devices or platforms. OpenCL provides a standard interface for parallel computing using task and data-based parallelism. C and C++, which have a wide user base, make it easier to get started with OpenCL. The main advantage of OpenCL code is that it is intended to be portable across different platforms. For example, using pure OpenCL, the same code for FPGA should be able to run on a CPU OpenCL target. However, it should be noted that performance is not portable across platforms. The same OpenCL code optimized for one platform is unlikely to be optimal on another platform. So while the same code can be reused, it is likely separate optimization effort is required for each platform. Despite this, OpenCL is still a useful abstraction for targeting FPGAs. We'll go through some basic definitions first from the FPGA perspective. Remember, the model we are considering is a host CPU and one or more FPGA accelerators. The host is the host CPU, and the host code is the code that will run on this CPU. This controls the accelerator and manages the hardware kernels and data transfer between CPU and FPGA. The kernel code is the code that gets converted to a hardware kernel that will run on the accelerator. In the OpenCL context, an OpenCL platform is a data structure that identifies a vendor's OpenCL implementation. The host code will use the OpenCL platform to access and use a specific FPGA device. The Xilinx platform is the static part or the shell on the FPGA device. The shell includes all the interface IP and logic to enable the FPGA to communicate between host and kernel. For example, the shell will include the PCIe core, memory controllers, and a management interface. On the right, we have a representation of the OpenCL memory model. OpenCL only defines how OpenCL objects interact with various memories. How these memories are physically arranged depends on the target platform. In the case of the FPGA platform, multiple levels of memory hierarchy are supported, from off-chip, external DRAM and high bandwidth memories to on-chip memory elements. In our model of host CPU plus FPGA accelerator, the host memory is usually the DRAM in the host computer or server. Only the host program has access to this memory. Global memory will be visible to host and devices and is accessible to all items in a workgroup. This is usually memory connected to the FPGA accelerator platform that can be accessed by the host CPU over the PCIe connection and also by hardware kernels in the FPGA. Constant memory is simply a read-only region in this global memory. A local memory is connected to a workgroup and shared by all workgroup items. Private memory is memory that is only accessible by a work item. On an FPGA, local and private memory can be implemented in on-chip memories inside the FPGA. We'll consider 5 main parts to an OpenCL application. The first step to develop an application is to develop the host code. As we said, this runs on the host CPU and will dispatch hardware kernels to target devices or OpenCL platforms. The host application needs to have the following: a CL device ID, this represents the device, and each accelerator will have a device ID. CL get device IDs can be used to read back the CL device ID from your program. CL kernel represents a specific kernel. The FPGA binary may have multiple kernels, which will all be available when the device is programmed. So the CL kernel allows us to differentiate between multiple kernels running on the same device. The CL program represents the source where kernels come from. In OpenCL, kernels can be compiled on demand. In practice, for an FPGA, you will likely only ever use pre-compiled kernels, but the CL program is still a part of the OpenCL application. The CL command queue is used to queue operations for scheduling on the target device. The CL context enables devices to receive kernels and transfer data back and forth between them. There are 7 main steps for application execution on a heterogeneous system. The first step is powering up. We then initialize our runtime components. We then configure the device or program the FPGA with the XCL bin. So this contains your hardware kernel or kernels. We then allocate and initialize memory buffers on the host side. The next step is to write the buffers or the data to the target device. We can then run the accelerators and synchronize the results of the computation. Finally, we read back results from the buffers in the FPGA memory to our host. On power up of the host server, the FPGA platform is powered on and is automatically configured with the shell. The shell includes the PCIe interface. It automatically communicates to the host during the boot process, indicating the target is available. The shell abstracts the FPGA I/O, the input-output resources, to the hardware kernels. In this case, the PCIe interface is abstracted and standard AXI interfaces are available from the shell to connect to your hardware kernels. A shell is stored as firmware in non-volatile memory on the FPGA board and can be updated as new versions are released. If the shell is updated, at the next power on after a reboot, the board will be initialized with the new shell. Once the system is powered on, a host program can be run and create an OpenCL context. This consists of registering the platform and FPGA device and opening a command queue to start servicing the device. There are OpenCL APIs to discover platforms and devices, and APIs to create context and command queues. During configuration, hardware kernels are loaded on the device. The FPGA binary, the XCL bin, is used to program the custom logic. The kernels are now ready to be executed on the FPGA. Next, the application needs to start sending data. In this example, 3 buffers are shown. 2 are used to send data to the kernels, they are read by the kernels, and 1 buffer is used to store the result. These device buffers mirror buffers already allocated on the host, where the input data is already stored and where the output data will be written back to. Data can now be copied to the device, or more accurately, to global memory accessible from the hardware kernels running on the device. The buffers are then associated with the kernel using the CL setKernelArg API, and the kernel is started using the CL enqueueTask API. The hardware kernels then execute. They can read data from the input buffers that are now in global memory, and they can perform their computation. Results are written back to the output buffer or buffers, still in the global memory. When the kernel completes operation, it automatically notifies the host. The kernel done signal is registered in the command queue. When the host is ready, the last step is to copy the results from global memory on the FPGA accelerator board back to the host. This concludes one complete execution of the kernel or kernels. After reviewing this OpenCL execution model, you should now have a good appreciation for how the device operation is sequenced from the host code and how data is moved through the system.